Volcano. Molten lava. Hot enough to set fire to anything in its path. A river of rock. What do you think is the hottest thing on Earth? And how do we tell how hot things are? Ice melts at a temperature of exactly 0 degrees Celsius. Inside a fridge, the temperature is between 0 and 5 Celsius. A healthy person has a mouth temperature about 37 Celsius. Butter melts between 30 and 50. Pure water boils at exactly 100 degrees Celsius. To fry chips, the oil has to be hotter than 100. Why do you think the chips sizzle so much when they first go in? Could you cook chips in the oven? When you switch it on, a light bulb filament heats up to over 2000 Celsius. If we make the picture darker, you can see the white-hot filament in the middle. But bright as it is, the sun outside is brighter still. The sun makes energy by nuclear fusion in the plasma inside. Could we do that too? Russian scientists invented the tokamak, based on this British machine, which had reached 20,000 Celsius. Some plasmas are easy to make, like the ones that give the colour to these signs. But to have a chance of getting them hot enough for nuclear fusion needs a lot of money and effort. How hot can they get? In this tokamak, 10 million Celsius. In the latest experiments, the plasma has reached more than 40 million Celsius, the hottest thing on Earth. How do we measure temperature? When you've got a complicated object, it can be useful to have a thermocamera. But what does this picture mean? This optical pyrometer can be used to measure the temperature of anything hot enough to glow, like a furnace. Inside the machine is a V-shaped filament. When it glows the same colour and brightness as the furnace behind, they're both at the same temperature. So the furnace is at 1260 Celsius. How would you measure the temperature of a candle flame? What about the furnace in a power station? Why couldn't you stick a thermometer in? how hot is this pan? And how would you measure the temperature of a river of rock? This is molten rock. But what about solids that aren't quite hot enough to melt? What can you do with red-hot steel that you can't do when it's cold? At about 1000 Celsius, even solid steel is soft enough to push into shape. In this forge, they use a drop hammer to push hot steel into shape, the right shape for axles for buses and trucks. And as long as it's hot enough, there's no problem in trimming off an inch of solid steel at the edges. It's as easy as cutting your fingernails. Bright yellow heat is over 1000 degrees Celsius. Orangey heat about 800, and you can see the liquid rock cooling down to dull red, about 500 or 600 Celsius. What temperature do you think this rock is when it goes up and when it comes down? What colours are cold? Flowing down this mountain is a glacier, a solid river, a river of ice. How quickly do you think it flows? Sometimes in cold weather you get icicles. How do you think they're formed? This liquid is boiling at minus 196 Celsius. It's liquid nitrogen. This ice cube is at minus 5 Celsius. For liquid nitrogen, that's very hot indeed. So the liquid nitrogen boils furiously, like water on a hot plate. Why do you have to keep liquid nitrogen in a thermos flask? Why does it boil when you stick something in it? And what will it do to the flour? What will happen to a balloon in liquid nitrogen? And what do you expect when you take it out again? Temperature doesn't go down forever. There's a lower limit at -273 Celsius. It's called absolute zero. When you get near absolute zero, funny things start happening. Lower a magnet into a lead dish and it just sits on the bottom. But close to absolute zero, the magnet won't settle. It just floats there. This is liquid helium, which boils only 4 degrees above absolute zero, or 4 Kelvin. At exactly 2.19 Kelvin, the helium suddenly becomes superfluid, so runny that it flows straight through the solid white plug. When liquids cool down, they freeze and turn into solids. It doesn't have to be freezing for liquids to freeze. How do liquids freeze? Many turn into crystals. These are crystals of one pure substance. You can't always see them as clearly as this, but in fact lots of everyday solids are made of crystals: sugar, salt, sand, rocks, and even metals. These are crystals of pure zinc. But what about things that aren't pure? Butter's a mixture, not one pure substance, and butter doesn't freeze into crystals. You can find out whether things are pure by looking at how they freeze. This pair are observing the freezing of a pure liquid. First, they warmed it up, and now they're letting it cool, noting the temperature every minute. This pair have warmed up a mixture. Both the pure stuff and the mixture soon begin to freeze. The pure stuff has a freezing point of about 52 Celsius. The cooling curve of the pure stuff drops quickly to about 52 and then stays there for several minutes while all the liquid freezes. But the mixture cools steadily all the time. Mixtures freeze slowly over a range of temperature. This is a bullseye window. How do you think it's made? Red-hot glass. Is it a soft solid or a sticky liquid? Glass isn't one substance. It's made from a mixture of ingredients, in this case sand, soda and limestone. When they're thoroughly mixed together, they're melted in a furnace at 1200 degrees Celsius. As it cools down, the liquid glass begins to harden. So it doesn't fall off the blowpipes, but it's still soft enough to blow into shape, to make a lampshade, for example. Why do you think they use wooden moulds to shape the glass? Why do they keep them wet? And why do they keep twisting the pipe? Remember, pure substances freeze at one temperature. Mixtures freeze slowly over a range of temperatures. Can you work out why this is important for glass blowers? Hail comes hammering down in hard lumps, but snowflakes float down gently. Why are they different? They're both made of ice crystals. Have a close look at a snowflake. It's one big, beautiful crystal. Big crystals take time to grow, and snowflakes are formed by slow freezing in the sky. But now look at this big hailstone, formed in layers where rain has frozen on the outside. Lots of air bubbles and little crystals because hailstones freeze fast. Slow freezing gives big crystals. Quick freezing makes tiny crystals. What might that tell you about different rocks? This granite might have come from a volcano. So might this pumice stone. Which do you think froze more quickly? So, what experiments would you like to do if you could get near a live volcano? Why would it be useful to be able to predict eruptions? And what could we learn about the inside of the Earth by studying a river of rock?